And obviously, I'm going to talk about ionosphere. Ionosphere, what we are referring to ionosphere is basically the layer of atmosphere that has electrons in it. Basically, when sun hits the molecules in the Earth atmosphere, they excite the molecules and electrons skip, and we end up with some ions and some free electrons. And the density of the electrons in the Earth's atmosphere, or what we call ionosphere, it could be at altitudes of probably few tens of kilometers all the way to 1,000 kilometers. There could be free electrons, but usually the highest density is around 400 kilometers, 300, 400 kilometers. And since our SAR orbits usually are around 600 to 800 kilometers, then that high density of electrons are well below our SAR orbit, and we are then sensitive to them. And the way that it affects SAR data, actually, it affects SAR data in different ways. But basically, you can imagine the same equations that David showed for troposphere. It's just the same. The principle is the same. You have an electromagnetic wave, in our case, microwave signal is propagating through atmosphere, and the refraction index is changing, in this case, because of the electron contents. If we, on this figure, I'm showing on the left side the TEC maps, total electron content maps, derived from GPS data for 2 different dates. And as you see, these kind of maps are expressed based on the TEQ, which one TEQ is 10 to the power of 16 electron per square meters. And simply the TEQ is different for 2 different dates. And usually they are a function of daytime. Of course, at noon you have a lot of TEQ because there are more solar radiation and there are more activity. It's a function of season. It's a function of latitude. So we need, and since we are talking about rapid path interferometry, then we need to take care of this component. If we look at our interferometric phase, we can probably decompose it to different components. We can say 4 pi over lambda delta R, but that delta R is not only displacement. It's a summation of displacement, some geometry there, which we talked about mainly on first day, both on the theory part and also in the street map app part. Just because of the baseline separation, you get some geometrical phase, which we usually remove based on the existing DM and the knowledge of the orbit. But then there might be residuals. And then there is troposphere, which David talked about. And then there is ionosphere. And some other noise, maybe the correlation noise or scattering phase noise. The good news is, among these components at wavelengths that we are working with, only ionosphere most likely is mainly dispersive. By that, we mean that if the microwave signal is propagating through ionosphere at different frequencies, they are experiencing different delays. In this equation on the right side, you see that the range delay due to the ionosphere is a function of how TEQ has varied, some constant, and the frequency. And that's really how GPS is estimating ionosphere. Those of you who have probably, if you have worked with GPS, estimating ionosphere from GPS is very um, common processing step. We don't have that luxury yet. Hopefully we will in 2-3 years with InSAR to have different frequencies. But for traditional SAR platforms, including those which are now operational, we have only one center frequency. However, so if you look at the spectrum of one SAR image, one SLC, you can imagine something like this. You have a center frequency, that's the frequency that your radar is operating at, which could be C-band for Sentinel around 5.4 gigahertz, or for InSAR L-band, it will be around 1.27 gigahertz. So that's your center frequency. However, we have a bandwidth. It's a band-limited signal, and we have a bandwidth. So we could, what we could do is to simulate something like what GPS is doing, basically getting to two different frequencies. We could just band pass this signal and get to a lower band and a higher band SLC. So basically from one full band SLC, we get to two different SLCs at the lower part and higher part of the spectrum with different center frequencies. And we could do that for the the secondary image also, and come up with two other SLCs. Now we can, similar to what we did before, we could make interferograms. Now, instead of two SLCs, we have 4 SLCs. We can make one interferogram from the low band SLCs and one interferogram from the high band SLCs. And you can go through the equations and get to these two equations, which basically separates the dispersive part of our interferometric phase, which in this case we assume it's only ionosphere, and that could be explained with this equation. Here F0 is the center frequency of the full band FL, and FH are the center frequencies of the lower band and higher band, and the interferometric phases at lower band and higher band. And the non-dispersive part is really the sum of all other components. So this is the good news. Then this means that without relying on models for ionosphere, hopefully we can think of a solution. Here is one example that is in a paper that we published a few years ago for Maule earthquake, magnitude 8.8, somewhere in Chile, 2010. Here is an interferogram. It's around 400 kilometers by some 100 kilometers. There are all these fringes, and there was an earthquake. We know there was a big earthquake. However, when we estimate the ionospheric phase, we see that, okay, these fringes are quite a lot from ionosphere and some from the actual ground displacement, which now makes sense because here is the trench and you expect more fringes close to the trench, and then the density of the fringes should decrease. That's not what we see in the original interferogram, but after correction you see that pattern. Now let's try this technique. It has been implemented in ICE2 for StripMap app and also for TOPS app. Now we are trying to, in this notebook, we are trying to use the Hawaii data, LOS1 from Monday, and change the configuration file to apply the ionospheric phase correction. Feel free to follow the steps. It shouldn't be too processing expensive, so we're gonna go together if you want. Around the first step, we simply sets up the directories and the general setup, and then make sure that where we are at the work, Hawaii LS1 directory, and then run the next cell, which if you have OpenStar Lab doesn't have the OpenCV installed, so with this command you can install it, and we need that package for doing some filtering. It should be done fairly quickly. And the next cell is just configurations. The reference.xml and secondary.xml don't change. However, the strip-map.xml strip-map.xml needs a little bit change. I'll tell you what change it is exactly. And here is the exact changes that we are making. We are adding a step called do split spectrum true and do dispersive true. Obviously, the first one is gonna allow to split the spectrum, and the second one is gonna do the ionospheric phase estimation. I think there is one student that cannot hear me, but I assume rest of you guys can hear me.
Yeah, I'm trying to determine that myself. It seems like most people can hear fine.
Yeah, okay. So I'll go forward, and just note that there is one extra step that I'm not turning it on. It's off by default, but I'll get back to it in the end of the notebook. And to be clear, which steps are we adding? If you look at all different steps that StripMap has, on Monday, we skipped split range spectrum and obviously subbanding, resampling the subband SLCs, making subband interferogram, whatever is red, we skipped on Monday. And now with those two options that we added to the stripmap.xml, we are gonna try them today. So go ahead and run this cell, which basically splits the spectrum, the range spectrum of both reference and secondary SLCs. It shouldn't take that long. This step is the only multi-threaded step, but last night I tried and I checked, it was using 8 threads. So hopefully won't be like what you guys experienced on Monday for Topo. So different instruments, while the range spectrum, splitting the range spectrum is going on, different sensors have different bandwidth, and the range resolution of your SAR data, as probably you have noticed from the theory part, is a function of the range bandwidth. And by band passing and creating band passing the spectrum and creating SLCs with smaller range bandwidths, basically we are reducing the range resolution. But that's fine, because anyway we are using these subband SLCs only for estimating the ionospheric phase, which anyway needs smoothing and filtering. So in that sense, it's fine. However, you need some bandwidth. What we have tried at best was 14 megahertz for LS1 SLCs over very high coherent regions that might work. we got it to work, but it might not work everywhere. And one other thing that is important is really the accuracy of this method is limited by the total bandwidth, because if you, in the paper that we have and others, including France, there are variants of the estimated ionospheric phase as a function of the variance of the interferometric phase, and you will end up with an equation that is driven by the total bandwidth of the data, which actually defines this distance between the low band and high band. The more distant the lower band and high bands are, you get better estimates, because that's in the denominator, and it makes the variance much larger when they are closer. So just okay. This step for me is finished. So I'm gonna take a look at the directory. It should have created the split spectrum directory, which has low band and high band subdirectories. If we look at each of them, we see similar SLCs that we saw on Monday for the full band, but now they are just we know that it's only part of the spectrum. These SLCs are before co-registration, so now we want to resample them. I'm gonna hit the run on it. All it's happening right now, very similar to what you saw at the StreetMap app and also at TOPS app. When you have two SLCs, reference and secondary, you need to resample, co-register them. The co-registration parameters are the same, so we are not gonna estimate, compute the offsets again. We are gonna use the offsets that we had already computed, but we are gonna use that to resample the subband SLCs. No, without changing the environment to 8 cores. Last night I tried. The module was respecting the environment and was using 8 cores by default, 8 threads. So I think you should be fine. The ionospheric correction is available in the StreetMap app, which supports not only ALOS but any StreetMap app sensor. It could be any frequency, whatever that StreetMap app can process. The TOPS app supports also ionospheric phase estimation. So basically, it's not. Yeah, you have the option to apply for Sentinel also. Not for the stack processor, no. We are working on that, but we don't have it right now. Yes, for Sentinel, it's pair by pair right now. All right, so now that we have the co-registered SLCs, then we can just make the interferograms. In this case, we will end up with 2 extra interferograms, one at the lower band and one at the higher band. Go ahead and run that step 2. 48 threads on which step? On geocoding, maybe you are at the end. I don't think if we even have 48 threads.
Some of you actually do.
Okay. Wow. Okay, so if that's the case, then you may want to yeah, feel free to use the same comment to limit the threads to 8. Yeah, maybe I misunderstood the question. I think David answered. Yeah, it's any microwave signal propagating through ionosphere is gonna have the ionospheric delay. It's just it's smaller for higher frequencies. It's larger for lower frequencies. So for C band, for L band, it's like 18 times more than C band, and even less for X band. So it makes more sense to apply whenever you are processing L band, uh, but for C band, um, there is a recent publication, I think last year or the year before, from Caltech. Shunran um, showed that even for C band, at certain area, it matters to apply the ionospheric phase estimation. So for me, the interferometry part also finished, and now I have the low band interferograms, similar to what we had before, and the high band interferograms as well. So we are gonna go ahead. We need to unwrap them. So before unwrapping, we wanna filter them similar to what we did before on Monday. And it should be fast too. Any question while the interferogram generation is going on? I think while it's still processing for me, I think it would be useful for you guys. All right, that's finished. Then I'm gonna just display what happened. Basically looking at the low band, full band interferogram, low band interferogram, and the high band interferogram. And as you see visually, they are very similar. It's very difficult to see any difference, but actually there is difference. The difference is small. If you look at the difference between the two, I'm now showing the difference of the low band and high band, or maybe the difference of, the difference of the full band and the low band. And there is a small difference, but that's exactly that small difference that we are gonna rely on to estimate the ionospheric phase. So let's go and unwrap the subband interferograms. Somebody has problem with GDAL, looks like. Perhaps the easiest would be to... Anyone else has the same problem? So Garrett has the same problem. Okay, not everybody. Jessica. What do you mean, Ozzy, by fixing the path? The solved for you?
Yeah, so that was in The one where we had to change the directory because the soft link to the strip map was messed up. So before I had fixed the actual path to it, I was getting the does not have attribute error, but after I fixed the path, it seemed to work. So I don't know, maybe double checking the path could help.
Okay, so the main assumption here is the path is whatever the strip map app expects. I assume you guys changed the path to the Hawaii dataset to get it to work for the raster notebook.
Yes, we did.
Okay, so maybe something is messed up there. Yeah, perhaps the error that I'm seeing from Marnie, probably it's because the data is not there, so maybe it has failed even before that. Did the previous running the previous step worked for you? Okay, so the previous step has worked for you. That's strange. Can you check if if you just create a new cell and just make sure that where you are, I'll try it myself here after this step. Yeah, something like that. It should be somewhere like this. Okay, that looks right. And if you just say ls, do you see? Okay. Is there anybody that works? Yeah, I think few people said yes, it works. So I think I'll just go forward and maybe we get back to error messages. Now we have the subband interferograms unwrapped. And next step is really just to estimate the ionospheric phase using the equation that we showed at the beginning. So I'm gonna hit that button. And what is going on right now really is simple. It's just the equation that we showed at the very beginning here. That's what is happening right now. Estimating the ionospheric phase from the subband interferograms and given their frequencies. Can any of you guys who see that error, can you just close it and restart your notebook or something? Okay, so somebody, Marnie, I guess, says that she tried to run the previous cell again and then it worked. Maybe the thread is giving some of you guys problem. Yeah, there was a cell to install OpenCV at the top. Maybe you skip that one. Now I think previous cell was before unwrapping. All right, so that step is also done. So we should have the ionospheric phase estimated, and you see a lot of logging messages here and about iteration and masking and filling. And the reason for that is the estimated ionospheric phase is very noisy, and that's because of the limited bandwidth that we have. In this case, I think it was just 14 megahertz or maybe 28 megahertz, depending on which type of LOS1 data is. And this is the estimated dispersive part, or what we interpret as ionospheric phase, and the non-dispersive part. And you see that it's smooth because we did filter. And if the unfiltered version is also there, and you can try it to display it, and you will see that it's very noisy. So smoothing is always part of this process. By default, we don't remove the estimated ionospheric phase from the interferogram, but just since this was the first time that we had it available to users, so I want you guys to explore it also more. But if you remove it yourself, which is simply the interferogram minus ionosphere, and that's what you have. On the left is the original interferogram, which ionospheric phase was not removed. On the right is the after removing the ionospheric phase. So this is important because all that long wavelengths, something like 4 fringes here, was actually due to the ionospheric phase. It's all gone. I'm not going to run the last step, which is geocoding, and you can run it yourself. I realized it was using a lot of threads, but basically what it all it does is just geocoding the outputs. And you can modify the filter parameters using your stripmap.xml if you want. The filter is a Gaussian filter using OpenCV. You can have it in different directions, can have different sigma, and you can even rotate it. Playing with the filter is available. And one other thing is ionosphere can induce azimuth offsets. And in that case, the regular co-registration won't work. So you have to turn on the rubber sheeting. This is the worst example that I have so far, where the interferogram was not even properly formed because there were significant azimuth offsets due to the ionosphere. This is somewhere in Chile. It doesn't happen everywhere. It's really when ionosphere is experiencing scintillation and high frequency thick gradients. And the correlation is affected, the interferogram is affected. After accounting for those offsets, we get nice interferogram and the correlation looks much better. But by turning on the rubber sheeting, that should be fine. So that's all I had for this part of the atmosphere session. I saw that many people actually had problem. So
yeah, I was going to ask if you had any ideas. Maybe it's the OpenCV, but some people are saying that they ran it, they installed it, and it's still not working.
Yeah, but if it was OpenCV, that would be the import CV2 would give them an issue. But I saw only one person with that error.
Yeah.
Uh,
What's the libgl? That's part of OpenCV, or is that something else? Importing of.
I'm not really sure. The low pass, whatever breaks that low pass filter, that's OpenCV.
So it shows the CV2 failed. So perhaps people forgot to install it, or maybe they ran through it and then installed it and ran through it again, and that caused some problems.
Yeah, it's at the very top here. Can someone try? Garrett, I saw you said that you got the same error. Would you please just try?
I did it. It ran.
It runs now?
It ran before.
Oh, we thought your response before was that it failed for you, so it ran for you.
No. What I mean is, I ran that step and it still failed.
Yeah.
Oh, okay. So it still fails. I think I don't know why.
Oh, interesting. And now I get the same libgl error when I run the ionosphere step. That's interesting. I was a little behind. Huh.
Okay, so it looks like I'm the only one who could run it. Maybe if I close it and open it, I won't be able to run it. That's interesting.
Interesting.
I don't think if I have changed anything in the notebook, I'm just using the exact same notebook. So I'm on the server.
So Gareth, yours ran all the way to the end?
No, it crashed at ionosphere step.
Okay, so I think we're all experiencing the same thing with this libgl.so.1 error.
Yep. And it just crashed again for good measure. I ran it in the terminal.
Oh, okay. Looks like I have changed something. Oh no, that could be just my wrong. Never mind.
You're running on OpenSAR Lab, aren't you, Paresh?
Yes,
Yeah.
yes, definitely. So then nobody has been able to run through.
Yeah, I don't think anybody's gotten beyond the ionosphere step.
Okay.
So where is that code cell that's failing for other people? I don't even see it.
It's cell 22 if you started at the top and just ran through it. It says stripmap app.xml -- start ionosphere -- end ionosphere.
4.06. Yeah.
Okay.
You said 22, Paul?
Yeah, for me it's 22.
Oh, okay, yeah, of course, because I did.
Right, yeah, you might have added it too. Actually, I added
Okay.
OMP num threads, so different for you.
20, yeah, it should be 20, yes, cell 20.
Yeah.
Okay. All right, maybe we can. It will be difficult if I cannot reproduce the error. What I will do is just I will make sure to pull these two docs again.
Maybe the homework can be that somebody fixes it.
Yeah, I was hoping the homework will be to try it on a different data set for some strip map data set. But since they haven't been able to run it right now, then yeah.
Yeah, so maybe focus on the modeling exercise for homework for tonight.
Yeah.
And this one will hopefully resolve before the end of the class. They're running for everybody. Sure, it's a simple thing.
Okay.
Great. We almost made it.
Almost.
So two more steps. So actually, that's the last step, isn't it? Is when you plot it,
Yeah.
you geocode it. So it's very close.
Right. Yeah, I'm not sure because I'm really using the same notebook.
Yeah, that seems almost impossible since the environments are the same and the notebook should be the same. But reality is what reality is. Maybe the library that we just pulled changed somehow in between when we did it.
I hope not. I don't think so.
Yeah.